Okay, random rant over. Today marks the last lecture really in sort of theory before we move on to actually having a look at how do we actually interact with databases. So as of next week, we're going to start looking at SQL. I'm aware that we've gone through a lot of this quite quickly, and realistically, having looked at it, there isn't a great deal of choice. A lot of what you're taught would cover over an entire year in a lot more detail, so we're kind of rushing through it, but hopefully it will all make sense. So today we're going to have a quick look. We're going to finish normalization. We're going to have a look at the example, which I'm sure you all have done over the last couple of days. Quick recap on keys, just so that makes sense. And then finally, we're going to talk about the last element of design, which is the physical design part of the database. So these are the kind of things that we're going to chat about today. Feel free to use today's meet, ask any questions as we go along, and I'll check it at the end. One of the things you will need next week, or certainly the week after, is going to be a MySQL account. You're going to need access to MySQL to actually create databases and execute SQL, all that kind of stuff. ECS will provide you with this. We offer a hosted account where you can create it using the self-service portal. Please go and do that. There's instructions, detailed instructions on the resources tab under QOL for this module, but it really isn't rocket science. You just go and request an account. Some of you might have done that already for other modules. If you've already got an account, that's absolutely fine, but you do need to create one ready for the work we're going to do. You can install MySQL on your own computer. Nothing to stop you doing that, or your own server, or however you want to do it. But the ECS hosted account is the one we will support and the one we will use for our assignments. And you can access it from anywhere. It's not one of these resources where you have to be on campus. You can access it via a thing called PHPMyAdmin from anywhere. So please have a look, go on, create an account if you haven't got one already. So a quick recap then on normalization. So normalization is what we were talking about on Tuesday, and Wikipedia's definition has a whole bunch of text in there, which is all very meaningful, but if we cut it down, the two key things, the reasons why we normalize data, is to reduce redundancy in data, so to reduce replication, reduce unnecessary duplication, and to improve integrity, because when we have poorly related, uncontrolled, duplicated data, it very easily gets out of sync. We lose referential integrity. We have 15 copies of your telephone number. You change your phone number, we update it on 14 of them, but the 15th copy doesn't have it. So what we try and have is we have one copy of record of every bit of data. We have one copy of your phone number, one copy of your photo, one copy of your marks, and then everything else references it, which is the relational bit in relational databases. We will go to third normal form. So this is a process which we use to go from unnormalized form, UNF or 0NF, through a series of steps. So we first identify our repeating groups and we move them into separate entities. We then identify part key dependencies and split them into separate entities, and finally non-key dependent attributes which link in, and we go through and do that. So this was the second example that I left you with on Tuesday, which I'm sure you all ran off and had a go at least. One of you? I'm sure you all did it. I have every confidence and faith. So let's have a quick look. So this is an example form, the kind of thing that you might expect when you come to your class test, that we give you something like this and ask you to, first of all, turn it, identify what's the unnormalized form, what are the fields in it, and then turn that into 3NF via first, second, and third normal form. So here is the sort of working out. So we start off in unnormalized form. All of this will go on Queen's Online. I'll put the answers up in that version. We have an invoice number, we have a date, customer name, customer address, and then we have a repeating set of fields with a pet name, a procedure, and an amount. So what did the poor dog have done to it, which dog, and how much did it cost to do whatever we did. So the first normal form is we remove repeating groups. So the repeating group obviously is the procedures, where we list name, procedure, and amount. So we'll split them out into a separate entity there, in this case the sort of procedure entity. And we have a composite key here. So we have an invoice number, a foreign key, which we know, which is going to be linked to this. And we now have a pet number that we've created as a primary key that we can use. And we split out the pet name, the procedure, and the amount. So that's the first normal form. We've removed the repeating group. Second normal form, let's look for part key dependencies. So within the pet, or the procedure, the second entity there, we have a name of the pet, and the name of the pet relates to the pet number, not to the invoice. It doesn't matter unless someone changes the name, it's not called Fido one day and Biggles the next day, so the pet name only relates to the pet number, which is a part key dependency, so we gain, to go into second normal form, we split that out. So now we have three entities, we have the invoice, we have the pet number and the invoice linking in the middle, and then we have the pet number, which gives us the pet name, Tiddles, at the bottom. Third normal form, what we're now looking for is we're looking to split out as much stuff as we can that where attributes rely on non-key attributes. So some of this is obvious, some of it less so. So the first one is, let's have a look at the customer, the invoice entity at the top. We have a lot of detail in there. We have things like the customer postcode, customer street, customer city, and we could arguably say that those depend on the customer. So the customer postcode, street, city, name, all of that kind of stuff depends on the customer, which is not a key for invoice. So we can split that out. We can split that out into its own entity, in this case customer, give it its own primary key, and link that back to the invoice. And the second thing is that in the second entity there, where we have pet number and invoice number, the procedure and the amount, well, the amount and the procedure, the name of the procedure, are not actually linked to the invoice, or to the pet, sorry. They are linked to the invoice number. So when the procedure happens, it's linked to the procedure. The amount the procedure costs is linked to the procedure. We're not going to charge differently whether it's Fido or Biggles to have a splinter removed from his paw. Those are all the same. All the procedures have the same cost. So those then depend on non-key attributes. So they are then split out, and we end up with 1, 2, 3, 4, 5 entities at the end. We end up with an invoice. All that has is the date, and we know the customer. We have a customer, which has all the customer details in, now all dependent on the primary key in the customer number. We have the list of the pet, the invoice, and then what procedures were done on that, so it's linking the pets and the invoice with the procedures done. We have a description and a cost of the procedures that are linked in, and finally, for every pet number, we have a name at the bottom. So that's how we split those out. And you will be pleased and delighted to know that on Monday you will be doing quite a lot of normalization exercises, so this will become second nature. Doing this kind of thing, following these rules, is something that it's important to have as a kind of foundation. The reality is that in 5-10 years, once you're all cut and thrusting IT professionals out in the real world, you will probably do what I do, which is very rarely remember the specific rules, but it becomes kind of second nature as you look at a data problem and you think, well, actually, I don't want repeating data. I want one copy of it, and that's the rule that you then apply, and you break everything down. You end up with things in third or fourth normal form, but you don't have to follow very specifically the rules. You just use logic and your finely honed minds. So this was the schema then, in our sort of standard schema form that comes out the end. And these slides, I'll update the previous ones which have the question in to have these answers in as well. I think these slides are already up with the answers on, in case you want to follow it through, and you might want to refer to them on Monday when we go through. So let's just quickly go back again and have a quick look at keys. We had a couple of questions on Tuesday about keys in terms of what's there. So a primary key is an attribute or a combination of attributes that uniquely identifies an instance of an entity. We have entities, right? And once we have successfully put them into third normal form, every entity is uniquely identifiable. If I just have a collection of pens in unnormalized form, there's no easy way for me to refer to each individual pen. They are just a collection of things which I can't refer to. By the time we've normalized them, one of the rules is that every instance of an entity has a unique identifier. There's some way to uniquely reference each pen. Each pen has a serial number, each pen has an identity. And so every entity in our system has a primary key. Now, as I'll come on to, that could be one key, a simple key, or it could be a complicated or composite key. So primary keys are very useful, they're unique, they identify whatever we're talking about, that desk, that car, that student, that staff member. They identify them uniquely, and that references only that person. So a simple key, really obvious, is one entity. We look at an entity relationship diagram, we look at the entity and its attributes, and we find that there is one thing, and one thing alone, that uniquely identifies it. Student number, driving license number, car registration number, these are all useful things that when we look at something we find, oh great, there is already something there. There's an identifier which uniquely identifies that instance of the entity. That's a simple key. And in our diagram, we put it in and we put it in bold. So a simple key is a single attribute that uniquely identifies individual instances of an entity. However, life is often not quite as simple as that. And we often won't have data that we're getting in and data feeds that contain keys. So we often have to look at other ways of identifying them. So the first thing we want to do is we have a look at our data and we say, what are the candidate keys? What are the possible keys that could be used either individually as simple keys or in combination to identify this object? And we use those. Composite keys are more complicated then. So composite keys are where we say, no one thing uniquely identifies this instance, but these attributes in combination uniquely identify this instance. No instance has all three of these things the same. It might have one or two of the things the same, but it's not going to have all three of them the same. And that allows us to form a composite key and say, we uniquely identify that instance of this. Invoice number and pet number together for a procedure. The invoice might have many things on that goes to the user, so the invoice number isn't unique. The pet might have come in many times to have various bits of it operated on, so the pet number isn't unique. But that procedure, that pet coming in on that day for that invoice, together, the pet number and the invoice number are unique. So we look at them as composite keys, that those attributes in combination allow us to uniquely identify that person or that animal. In this case, imagine we were trying to identify a student and we have these attributes here. This is the data we're getting in, and there is no unique ID. Okay, we're getting a data feed in, and this is very common that we ask for a data feed. We want a list of students who have been, guilty of terrible St. Patrick's Day crimes in the area, have been fined for various things, a fake doctor's notes. And all these. I had a meeting the other day where we got a presentation from the disciplinary person for the university. There's some stories there. Someone faked 90 doctor's notes. They got caught when they said in the last one that they'd been in a coma for 3 months. They were at the university. They rang up, that's when they checked. They rang up, they were all fake. Apparently, I thought they would give a creative writing degree, but no. Anyway, right, so we have a data feed that comes in, it contains students, they arrive, they are poorly ordered, right? We have no unique identifier. We get in dirty real world data. So in this case, what I'm saying is for every student, sure, we have a name, we have a date of birth, so we can calculate an age from that, and we have an address, and the address is a composite of house name, number, street, and postcode. But we're missing some unique way of identifying the student. Now, we could just assign a number ourselves, right? Every student comes in, we assign another number to them, but that only works if we only get the data once. If what we're doing is every week we're getting new data about students, then we're going to need some way of uniquely identifying that this relates to students in our system. So we try and find a combination of these fields that is unique. And in this case, I would say that the name, the date of birth, and the address fairly should uniquely identify you as an individual. I think it's quite unlikely that someone of the same name and the same date of birth lives in the same house, at the same place. So these fields together uniquely identify you. They can become a primary key, and from that we use them as a composite key. So they become a composite primary key. So primary keys uniquely identify an entity. Foreign keys uniquely identify another entity. So everything in our normalized data has a primary key. Everything can be uniquely identified. You all have student numbers you can be uniquely identified. We might store records, and within a record of a piece of work submission, we would record your student number. And that is referred to as a foreign key. So within our student number, within our hand-in, our record of your submission, the primary key is a submission number, but we also store the student number. It's not a primary key, it doesn't identify the submission, but it identifies a unique instance of another entity, in this case a student. So a foreign key is something that exists within our data that uniquely identifies another entity. So it's a primary key somewhere else, basically. In another entity, it's a primary key. In this entity, it's a foreign key because it means that it relates to something else. And when we write that down, we put it in our format, what we see is we get the ampersands on the end. So if we had a couple of entities here, so we have module code, lecture code, and location code. So we have some details about the module in the first one on the left. Module code, which is the primary key that uniquely identifies the module, title, level, description, and we store in foreign keys of lecturer code, so who's teaching it, and location code, where it's being taught. We have a lecturer entity. Lecturer code is the primary key, title, name, when did they start, where's their office, how much could it cost to bribe them in order to pass. And then we also have a location entity, some unique identifier primary key for the code, and that would probably also know what's the building that it's in David Keir, what's the room number it is, that kind of thing. So we'd link those together. So in terms of the foreign key, you'll see on the left-hand side here that we have our lecturer identified. Now, in the module, the lecturer is not a primary key. The primary key of the module, the unique identifier for the module, is the code of the module. Lecturer really couldn't be the primary key for the module because, like, you know, we might teach a number of modules. We might teach no modules, or there might be a module where you teach yourselves. Who knows? But the lecturer code is a primary key for another entity, for the lecturer entity here. So we're using the primary key of one entity in another entity, at which point it becomes known as a foreign key. So it's foreign, i.e. it doesn't relate to an entity, this entity, it relates to another entity over there. So that is how foreign keys work. It's a primary key of a different entity, something else we're referring to. It's foreign to the entity that we're in. Simple. So that was a quick recap. Normalization and keys. That was a sort of cut down version of the stuff we went through before, just to get the grey matter working. So over the last 3 weeks or so, we've had a look at how do we design databases. And we've had a look at the 3 stages that we go through. So we start with the concept, a general dream. I have an idea, I have this system, and I want to model it. And at that point, really, all we're interested in is what are the entity names and what are the attributes. So I want to model this car dealership. Well, okay, what are the entities? So we have cars, customers, salesmen, servicing. What are the things that are happening? And for each of those, what are the entities? What data is stored about those? So we have a car registration number, model, type, color, mileage, all of the other associated bits and pieces. So that's our conceptual model. That gives us the idea of what is the actual concept of the data system that we're modeling. Moving forward, we then go to the logical level, and that's what we've looked at up until now. So the logical design takes, sure, okay, entity names, entity relationships, but let's start thinking about what are the attributes. So sorry, actually, it's been a long week. Let me start that again, just forget that ever happened. Conceptually, it's entities and the relationships between them, not the attributes. So we have our car dealership, see, I'm rewinding well, right? We have cars, salesmen, we have relationships between them. A salesman may sell a car is sold by one salesman, but a salesman may sell many cars. So we have our relationships, we have the cardinality of our relationships. Each dealership may have many different cars, each make may have many different cars, but each car only has one make. So we start mapping out the one-to-many, the one-to-ones. Does it need to have one? Could it have 0? How many is it going to have? So that's our conceptual idea. We think about things as entities. What are the relationships between them? So we have very, very high-level diagrams. These are the entities, and every car has one owner. It has potentially at least one driver. These kind of things go in. Moving into then the logical design, we start thinking about the attributes. So for every entity, what are the attributes involved? So we have a second-hand car salesman. Is how slicked back is his hair? How many times has he been bankrupt? How many dodgy deals does he have? All these kind of things get recorded. So for every entity, what is the data about that thing we're storing? What are we storing for the car? Say mileage, make, color, model, that kind of thing. And what are we storing for the dealership? You know, how many cars on site? Can we park it? Do they service? Do they sell different things? Do they sell electric cars? Whatever attributes we want to store with the data. And at this point, because we're mapping out attributes, we also start thinking about the keys. What are the primary keys? So we've mapped the attributes for our entities. What are the candidate keys, and which one of those can be primary keys? Which one can we use to uniquely identify that? And we start thinking about what are the foreign keys, what are the relationships, what are the records going to be that we store between them. That's where we're up to now. And now we move to the last bit of physical design. So this is the last thing that we do immediately before we actually start implementing a database. So we start thinking now about, well, what are the table names, the column names, and critically, what are the column data types? How are we actually physically going to store the data on a disk? How are we going to create it in our relational database management system? And as I say, this is it. You know, we look at it, we dream, we have a concept, we map that out, and now we come to the physical design. And the next step will be to actually start installing SQL Server, whatever we want, and actually installing it as we go along. So there's a few bits of terminology which are easily swapped and very easily confused within databases. And as we move from the concept where we talk about entities, we move into the physical realm, we talk about tables. And generally, these map one-to-one. Our entities, student, customer, car, are tables in our database. Our attributes, the things that we store data about in the entity, are fields within our table, columns, if you like, in our Excel spreadsheet of life. And an instance of an entity is a row in a table. So now we go from the idea of this kind of woolly logical design to the physical one, is how do we store it on a disk? So we have a file which is a table that stores the data within it. Within that we have these fields which are the attributes against which we store data. And finally we have a number of rows. Each row is an instance of our entity, is a car, is a student, is a holiday, is whatever it is that we're mapping as we go along. Up until this point, we've been really lucky because we have only been working in our minds. And our minds are wonderful places where we can call things fluffy, fluffy, foo-foo, cloud, exclamation mark, or whatever it is that we want. Once we start going to the physical, there are restrictions in how we name things. A lot of database engines won't allow you to have spaces in names. They won't allow you to have spaces in table names, databases, field names, that kind of thing. So we may well have a constraint in terms of how we name things. We might have called the entity A/B, and that forward slash or the dollar sign or whatever we want to use is not an allowed character. So we need to have those physical constraints. So we may well end up having to pull things together, get rid of spaces, call things different ways. In addition to any constraints that the actual database puts on us, we might really want in our business to have certain rules about what we call things. So we might well want to call every table, table X, table Y, table customer, table this, table that. We might have certain rules that they can only be 8 characters long, or they must start with an uppercase or a lowercase, or something like that. And just as you see different coding standards, which you've probably been exposed to, the idea that in Java, generally class names start with a capital letter, method names don't. We use camel caps, we use all that kind of stuff. There'd probably be some organizational rule when you create a database table. We use underscores instead of spaces, we use hyphens, we use camel caps, everything's in capitals, whatever. So you end up with a constraint on what you can actually call things. So we've gone from our entities where we just write the name and we call it whatever we want. we're going to have to constrain it as we go through and put the data in. The next bit is very important. It's all important, but this is extra special important. We have decided on the names, right? So we know our entities, we know our attributes, they are now tables, they are fields, they meet our naming constraints, we're all very happy. We now need to decide on some other information. We need to make some decisions on other bits and pieces around them. And the first thing we really need to decide is what is the type of data that we're going to store. Now, I don't mean what's the description of it. I mean what is the actual physical type of data that we store. So you're all Java ninjas, you've all done a lot of Java coding, so you don't need me to tell you that in Java there are different types of variable. We can have an integer, a float, a double, string, boolean, all these different things. And what that says is when we define the type, how much memory does it use? How many bytes does it actually represent in memory? And how does it store it? How does it save it? And databases are exactly the same. So when we define a field type, that allows us to store it efficiently. It allows us to search it. It allows us to maybe do maths on it. I want to know, I want to query things that are more or less than a certain number if it's a numerical field. Because what we could do is we could just treat everything as text, right? We could just say, okay, I've got name, address, date of birth, marks, module code. They're all text fields. You can put as much text as you want in. The database would store it, but it would be very, very inefficient. It would use a lot of space on the disk, which for small records no one cares about. But when you deal with hundreds of thousands or millions of data records, it adds up. And it would be incredibly slow to search. So what we really want to do is we want to try and find the best data type that matches the data that we're trying to store, because that will be the most efficient, the most accurate, and the quickest and easiest to search and exploit, which we'll come on to. So the type of data, as I say, it represents how they're stored, how they're searched, and what we can store in them. And this is also quite important, that if we have, say, an ID, you might naturally think, oh, that's going to be an ID number, right? Your student numbers here are ID numbers. Most people say student number, it's going to be a numerical value. Well, that's all great until someone comes along and puts an X in front of it or a Y because no one ever told them that they had to be numerical. So we need to try and think about ways of storing data which allow us to store all the possible data that we want to. And getting the right data type is very important for both performance, as I mentioned, the speed at which we can read and write and access data, but also for actual functionality. If we get the wrong data type, our database becomes unusable because we can't store data in it or we can't exploit the data that's in there. Now, nothing in life is ever simple, and database data types are no exception to that. Different database engines have different data types because people hate everyone. Database developers hate the world. If, like I've done, you've had to do development where you're taking data from an Access database, passing it through Oracle and coming out to Postgres, you will intimately know how upsettingly mad the difference is, not only in the types that they support, but also even in their formatting, that a date from one is not the same as a date from another one and goes along. So there are lots of different types of data. There's a degree of overlap. The simpler data types, which we'll look onto in a minute, things like Boolean, stuff like that, tend to be fairly compatible, but the implementations vary, and certainly when you get to the more esoteric and exotic field types, then things go mad, and it's easy for you to tie yourself in knots over it and lose the ability to take data from one source to another. Critically for this, we will probably later in the semester have a look at some other database engines. All of your assessment work in terms of the coursework submitted will be based on MySQL. So we're going to concentrate purely on MySQL data types. And MySQL is a very standard, industry standard database, and it's pretty harmless. There's nothing in it that you wouldn't, if you learned it, you'll come across Oracle later on. It'll all kind of make sense. So it's all pretty straightforward. We'll have a look now at some of the data types in MySQL. One of the things that's worth knowing is that we normally specify two things at least two things for a data type. The type of data and the length of that data. Some things we do, some things we don't. We give a length to it. Other things are automatically length boxed, but there's lots of references online, and it will all become clear. So let's look at some of the numeric data that we can store. So MySQL has a lot of different types of integer, even more so than Java. So we have a tiny int, which is a very small integer, range -128 to 127, if it's a signed value, or 0 to 255 unsigned. All of you, of course, immediately know why those numbers are there, because that's 8 bits, it's 1 byte on a computer, so it's storing 1 byte's worth of information as it goes along. We also then have small int, medium int, and int, obviously, which all have range. I haven't bothered writing all the ranges down here. And big int. And big int is a large integer, which you can see represents numbers from minus a lot to plus a lot. Many, many noughts. I don't know, I should have really put an exponent on that, sorry. But many, many numbers, right? We can do that. Those are the theoretical maximums of big int. However, just to even more make life difficult, that's the theoretical maximum MySQL has for big int. How it's compiled and how it's installed and how your operating system works may well limit that. So if you install that on MySQL on 64-bit Linux operating system, those are the ranges you will have. If you install it on a 32-bit operating system, obviously the ranges will be less. So these are the kind of limitations of things we go on. So I haven't put numbers on here, but generally, unless you are dealing with ridiculous data, big int is normally enough. Big int, if you run out of big int numbers, then you've gone quite mad. Float is a floating point number, a smaller floating point number, and double is double that precision. So it's a much larger floating point number that can go from sort of, I think, 39 zeros after it in terms of levels of precision. Boolean, very commonly used, is a yes or no value, as you'll know from Java, and it's synonymous to tiny int brackets 1. So I mentioned to you the length parameter, we can put that in brackets after things in MySQL. So tiny int 1 is saying, I want a tiny integer, and I want it to be one byte long. That's all we want. So it will store in the lowest amount of space. So we store booleans. If all we're ever doing is storing the number 0 or 1, we don't really want to reserve 64 million bytes or whatever it is a big int uses. We just want to use 1 byte to turn things on or off. And probably on some operating systems it will use 1 bit even. So those are the kind of numeric data forms. It's often a bit chancy, really. You know, you ask yourself, which one do I need? My default is usually to have my index is a big int, just because. Just because. Because I don't really want to have to run out of numbers at some point. So I tend to just define it as big int. It's not hugely wasteful. It goes in. Unless we're dealing with billions of records, we don't really need to worry too much about that. There are lots and lots of ways of representing dates and times and things like that within SQL. One of the reasons why we represent dates and times as specific formats rather than just a string with the date or time in will become apparent when we start manipulating databases. It's because the database itself is able to speed a lot of stuff up. So we don't need to look at each one. We can say to the database, give me all the records from the 2nd of July, and it will be able to do that without having to actually do text matching. So MySQL has a few different ways of dealing with the date. It has date, which is day precision. Date time, which is, as the name implies, a date and time combination. Precision to milliseconds, thousandth of a second. And there is also another date time format called timestamp, which is an alternative way to store date time, and this has picosecond accuracy to go in. There is a fascinating difference between them, which I will now bore you with ever so slightly, in that timestamp counts time since the 1st of January 1970. When you deal with Unix systems, we often deal with timestamps, and this is called time since the epoch. rather than storing a date as an actual year, month, day, time, what we do is we start counting from the 1st of January midnight on the 1st of January 1970 onwards, because nothing cool happened before the 1st of January 1970. What this means is we don't need to worry about the Stone Age, the oldie days, time before that, and it means that for the same amount of data, we can store an awful lot more precision, because all we're doing is counting the seconds and picoseconds that have happened since. However, it works great for me to take a timestamp today. What it's not very good at is for me to use a timestamp to record a date of birth in 1969, because it won't work and it will break. So those are, I know you're fascinated, those are the differences between it. And the epoch thing with Unix is very, very interesting, and it is going to break the world. There's going to be another millennium bug with it, but don't let me worry you. You'll be fine. The time, unsurprisingly, is a field that just records the time. So if we're not fussed about recording the date, we just want to get time that something happened, we'll record time to picosecond accuracy, and year is a year. It's just a 4-digit recorded number that records a year as we go through it. It doesn't record AD or BC, it's just AD year as we go through. So that's numbers and time and date, and the other type of data that we commonly want to store is textual data. So these are some of the text versions that go along, and the two most common, or the three most common ones are on here, is char, varchar, and text. Char is a character array of a set length. We say, I want to store data and it's going to be this long. Varchar is a variable character length. We say we want to store data and at most it's going to be this long. Now you might wonder, not unreasonably, what the difference is between them and why we care. So when I allocate using char, I'm always saying give me at least this much space in the disk and on memory. So if I allocate a field and it's char 32 length, every record will have 32 bytes of data allocated to it. If I allocate a varchar 32, what happens is it will allocate up to 32 bytes depending on the data that that record holds, plus 1 byte that records the length. So for some things where we have a fixed length, char is the obvious choice. If I want to record a ID number or something like that, and it's always 8 digits, char 8 is logical. Char 8 means we use 8 bytes to record 8 digits. It's always 8. The size is fine. If, however, I want to record someone's name, well, then the name might be Bob, or it might be something a lot longer. But I can't think of an example. Someone's got a longer name than Bob, I'm sure. And we would be very inefficient if we always said, well, what's the longest name we could store? Okay, it's 200 characters, let's say. We're always going to, in our database, on the disk, reserve for every person 200 characters every time for their name, because the vast majority of names are going to be a lot shorter than the maximum. So what we really want to do is we use varchar there, variable character array, where we say, okay, at most it's 200, but allocate only as much as you need for each one. So there's a little comparison on there that goes down, showing you if we store a value of a string, the difference in storage between char4 and varchar4. So if we have an empty string, char4 still uses 4 bytes. So whatever size you'll see, doesn't matter what we put in, we're always using 4 bytes. Varchar, on the other hand, empty string only uses 1 byte because the only thing it stores is the number 0 to say that it's 0 bytes long. When we start recording strings, however, and we go through, we have a 3-digit string, 3-character string. Char, still 4 bytes because it's always 4 bytes. Varchar by this point is 4 bytes because it stores 3 digits and the number 3. And then when we get to 4, it's actually using 5, so it's using more bytes because it stores all 4 and the number 4. So for most cases, when we have a very large set of data, we have a large maximum, but we're probably not going to use it, varchar is the logical choice. We also then have the text type, and text is an open-ended text entry, which could be pages and pages of text, hundreds of blog posts, huge amounts of data, and we have, again, some different types of text storage depending on how long we want it to be. Text is variable in length. It stores differently as it goes along, but it's incredibly inefficient to sort because it stores it in different packages and it moves it around the disk. So it's very slow to sort. So these are the textual inputs that we have. Character, fixed character, if we know exactly what length something is, might be the best choice. Varchar most commonly used because you just say varchar, and this is going to be the maximum. I don't want to take a name over 200 characters, that will break it. So you go in, and text where we want to store things. Generally, and I think newer versions of MySQL don't have this limitation, but varchar always used to be limited to about 255 characters. I'm fairly sure MySQL 5.4 breaks that and will go beyond it. But generally, the trade-off comes at about 200 characters, where you think, well, actually, I'm not storing one field, I'm storing a block of text here, and then you move to using text storage as we go along. We also have an enumeration in MySQL. So that is where you have a specific set of options. So I don't want to store a number. What I want to do is I want it to be one of a particular set. I want it to be you're a student, you're a non-student, you're on fire, you're not on fire, any of these kind of things that we put in where we have specific states, and it's going to be, we want it to be explicitly one of these states. That's the enum type. Same as Java, if you've done it. So the challenge, as I say, really is trying to look at this and trying to work out, what are the different data types and what is the most applicable and best data option for you to have. So we'll run through a few examples as far as I can see. So here we have some fields on the left, phone number, name, etc. And why and what I think in terms of the data type. So the phone number, really, most phone numbers, if we're dealing with UK phone numbers, is 11 digits long. All phone numbers in the UK are at most 11 digits long. You do get some smaller ones from these weird services that phone you up and tell you you've been in an accident. But generally, UK numbers are 11 digits long. So probably char fixed size is going to be an efficient way of working. However, if we then said, well, UK numbers are great, but we really want to store international numbers as well, well, then international numbers become quite a lot longer. I don't know what the maximum international number is, so I've made a guess that it's 16. It's probably almost certainly longer than that. I have no idea in different countries. So we could have tried char 16, or more likely, when we start getting to numbers that we're not sure how long it's going to be, we probably use a varchar there, because most of our numbers will be 11, but we want to store up to 64. Okay, let's use a variable length character array. Name, as I mentioned to you, usually that's the standard use of varchar. Maximum name length is, say, 255 characters. That's the biggest we're going to allow in. Most people will have a much shorter name, but there'll be 3 or 4 people that have huge long names, in which case we will allow it. Date of birth, it could be a date. There's no time involved. We're not asking, it's not date and time of birth, it's just the date of birth. So date is the obvious character. Password, again, probably a varchar, because some people's passwords will be short, ABC123, like my one is for the school network, or they will be quite long and complicated. If any of you know anything about passwords, you also often do a thing called hashing the password. If we hash the password, it's actually going to be a set length. So it could be 32 or 255 characters long, so we might consider storing it differently if we hashed it. Email address, again, probably going to be a varchar, because some people have ridiculously stupid email addresses. Some people have very short email addresses, depending on how quickly they got on board with Gmail when it launched. So these are all sort of relatively short bits of data. When we move on to larger bits, so I want to store an entire blog post. And a blog post could be, my lonely heart blog about, computer science and software engineering. It goes on for pages of ranting, and there might be pictures involved, and there might be links and this kind of thing. So we're probably almost certainly not going to fit it into 255 characters, so we probably want to put it into a text block, which allows us to fill it in. Finally, something like login retry limit. We're probably not going to have that very high. There's going to be a limit, on how many times we log in. It's not ever going to be like 1 million or any number like that. So we could certainly get away with some sort of integer, maybe even a tiny int or something like that, minimum amount to store it. In addition to deciding on the data type, we also need to decide on a bunch of metadata, a bunch of other decisions that we can make about these fields. We need to decide if they're required. Is it allowed for it to be null or it to be empty, yes or no? Or do we have to have an entry in that data? Is it going to be indexed? And indexing we come back to later on, but generally indexing just means, is it going to be quick to search? Have we pre-cached it? Is there a default value? If no value is put in, what is the default value? When I create a bank account, what is the default amount of money that's in there when I create a new account? And do we allow duplicates? Is it required to be a unique field? We've mentioned already that primary keys must be unique. So do we need this field or this combination of fields to be unique as it goes in? What we do with all of this is we build a thing called a data dictionary. So the data dictionary is the de facto representation of the physical design of the database. This is what will actually be implemented in the database. So in here, in our data dictionary, we take all of our information that we've made and we put in our tables, our fields, our types, and all of our additional and other information. And ideally, the data dictionary is what we update when we make changes. We don't just make changes to the database, we update our data dictionary and then we make changes through on the other side. And here's an example form. This is what you'll be looking at on Monday to have a look through it. And so it's just basically a list of fields. What's the database, the table, what are the attributes, what are their types, what's all that kind of stuff that goes in. I won't go through it in detail because, as I say, you will have a good look at it on Monday. And we are almost out of time. I can tell you're getting restless. Is that the impression I get? Don't worry, we're almost done. So just to recap, we have different levels of database design. We start off with the concept. What are the entities? What are the relationships between them? We then go into the logical. What are the attributes? What are the keys? And finally, we end up, as we did today, in the physical. What are the data types and how do we store it as we go along? Please remember, set up a MySQL hosted account because you will need it. Not early next week, but certainly the week after. Well, you will need it next week to follow along in the lectures if you want. This is what we talked about. It's 5-2. Go on, run like the wind. Thank you very much. I will have a quick